Hello, welcome to Science Reimagined. Let's go take a look at today's video.
Today, we are diving into one of the most, beautiful and downright bizarre ideas in all of science, Albert Einstein's special theory of relativity. This is the one that completely flipped our understanding of the universe on its head. And believe it or not, it all comes down to just one single, unbreakable rule. So, to really wrap your head around special relativity, you've got to accept this one core idea, that in the entire cosmos, there's a speed limit, and it's an absolute constant limit for everyone, everywhere. It doesn't matter how fast you're going, this one speed never, ever changes. And that unbreakable rule, well, it's the speed of light. Now, this isn't just some big number, roughly 300,000 kilometers per second. It's a fundamental law of nature. And here's the crazy part. Because that speed limit can't be broken, it forces everything else. I'm talking space, time, even mass, to become, flexible. It literally has to stretch and squeeze just to make sure the speed of light stays the same. Okay, to really see just how weird this all is, let's do a quick thought experiment. It's a super simple scenario, but it uncovers this deep, deep puzzle about how our universe actually works. And honestly, it's something that had scientists scratching their heads for decades. Okay, so picture this. You're standing next to a railroad track. A train zips past, and someone on that train throws a baseball forward in the same direction the train is moving. Now, if you're standing on the ground, figuring out how fast that baseball is going seems pretty simple, right?
Yeah, for the baseball, you just add the train's speed to the speed of the throw. I mean, that's just common sense. But what if that person on the train shines a flashlight instead? This is where things get weird. You'd think you would add the train's speed to the speed of light, but you don't. The light from that flashlight travels at the exact same speed for you on the ground as it does for the person on the train. It's always the same. And that one fact just shatters our everyday intuition about how the world works.
So this bizarre, unchangeable speed of light, it was a massive headache for physicists back in the 19th century. It just didn't fit with anything they understood. I mean, how could light possibly travel at the same speed no matter how fast its source was moving? They desperately needed an explanation. And their best guess? Well, they came up with this idea of a substance they called luminiferous ether. They imagined this invisible stuff filled all of space, and that light waves just sort of rippled through it, like sound waves through air. And if this ether was real, they figured they should be able to measure Earth's movement through it as we fly through space. You can actually see this long journey of discovery right here. For centuries, scientists got closer and closer to nailing down the exact speed of light, and it all came to a head in 1887 with the famous Michelson-Morley experiment. It was this brilliant setup specifically designed to find the ether, but it failed completely. They found absolutely nothing. No ether, no change in the speed of light, just that one stubborn cosmic constant. So you can see, physics was basically stuck. The rules of motion worked perfectly for things like baseballs, but they totally fell apart when it came to light. And that's how things were, until a young patent clerk named Albert Einstein showed up. He proposed something so radical, so out there, it changed, everything. Yeah, instead of trying to find some complicated way to explain away the constant speed of light, Einstein just embraced it. He said, okay, what if that's just how it is? He built his entire theory on two incredibly simple ideas, or postulates. First, the laws of physics are the same for everyone, period. It doesn't matter how you're moving. And second, the speed of light in a vacuum is the same for everyone, period. He basically took the puzzle that was confusing everyone and made it the new rule of the game. And from those two simple rules, oh man, that's where the truly mind-bending consequences come from. Because think about it. If the speed of light never changes, then something else has to give. And that something else is time and space. This leads us to a phenomenon called time dilation. It's this simple. The faster you move through space, the slower you move through time, at least compared to someone who's standing still. And let me be clear, this isn't just a feeling or some kind of trick of perception. Time itself literally, physically slows down for you. And look, this isn't just some abstract theory. We've actually measured this. The perfect test case came from a pair of NASA astronauts who also happened to be identical twin brothers, Scott and Mark Killey. Scott spent nearly a year up on the International Space Station, zipping around the Earth, while his brother Mark stayed right here on the ground.
So because Scott was traveling so much faster than Mark for that entire year, his personal clock, it ticked just a little bit slower. When he finally came back to Earth, he had aged about 5 milliseconds less than his twin brother. Now, that's a tiny, tiny amount, I know, but it's real, physical proof that time is relative. But the consequences of this whole thing, they don't stop there. Not even close. Einstein's simple rules also led him to what is probably the most famous equation in the history of science.
You all know this one, E equals mc squared. It's so simple, right? But this elegant little formula reveals a profound truth about our universe, that mass and energy are really just two different forms of the same thing. You could say mass is just an incredibly concentrated, packed up form of energy. Now, to really feel the power of this equation, you have to look at that c squared part. I mean, the speed of light, c, is already a huge number. Squaring it makes it absolutely colossal. What this means is that even a tiny, tiny amount of mass is hiding a staggering amount of energy. Let's take something simple, like a single paperclip. If you could somehow convert all of its mass directly into energy, you would release the power of 18 kilotons of TNT. To put that in perspective, that is more powerful than the atomic bomb dropped on Hiroshima. All of that energy locked away inside a tiny piece of metal. So, okay, we've got time slowing down, matter holding unbelievable amounts of energy. This all might sound like really abstract, out there, cosmic stuff, right? But the effects of special relativity are actually quietly at work in technology that you probably use every single day. Just take the GPS in your phone. How does it work? Well, it talks to satellites that are orbiting the Earth at about 14,000 kilometers per hour. And because they're moving so fast, special relativity kicks in. Their super accurate atomic clocks actually tick just a tiny bit slower than our clocks down here on the ground, by about 7 microseconds every single day. And that's not even the whole story. Einstein's other big theory, general relativity, adds another correction to the mix. So in total, engineers have to adjust those satellite clocks by 38 millionths of a second every day. It sounds like nothing, right? But if they didn't make those corrections, your GPS would be off by several kilometers in less than a day. The whole system would be completely useless. So, you see, from the clocks in orbit right down to the energy locked inside a paperclip, special relativity isn't just some wacky thought experiment. It's literally woven into the fabric of our reality. It showed us that time and space aren't some fixed, boring stage. They're active, dynamic players in this grand cosmic dance. And that just leaves us with one final, really tantalizing thought. If a rule as basic as the steady flow of time can be bent, what other so-called unbreakable rules of our universe are just out there, waiting for the next Einstein to come along and completely shatter them?